Hello, my name is Jonathan Sunday. I'm Strato's Chief Engineer for Draft Systems, and we're here today to talk about Strato's Selective Cushioning Unit. The Selective Cushioning Unit was designed to provide a more durable and adaptable replacement for hydraulic cushioning units to reduce hose separations and knuckle failures. By studying these symptoms, we've been trying to address and manage the broader root causes at play here. You can see in the cutaway view that the unit is made of a stack of elastomeric pads protected by a flexible housing of steel plates. These plates provide lateral guidance for the pad stack and protection of the individual pads from overcompression in an impact situation. The unit itself is composed of two individual assemblies. The draft pack inside the yoke operates in both buff and draft, providing up to 3¼ inches of draft protection for the knuckle. The buff pack in the rear is only activated in larger buff events such as yard impacts. Depending on the existing car geometry, the buff pack can be made shorter or longer for easier retrofit application. An EOC 9 retrofit would give 7 inches of total buff travel, with an EOC 10 retrofit giving 9½ inches of buff protection. You can see in the center of the graph, the unit sits in its neutral position with about 30,000 pounds of preload contained within the unit itself. As the unit is compressed in either direction, the pads provide an increasing amount of force, giving the appropriate amount of cushion for the situation at hand. The solid-state design accomplishes this without any mechanical components moving under load like a draft gear, without any hydraulic fluid like a conventional end-of-car cushioning unit or EOCC. The smooth force application of a solid-state design provides the energy capacity of 2 draft gears in draft and up to 6 draft gears worth of energy in the buff direction, all while maintaining the existing pocket length already in the car. If you have a given amount of force over the road, selective cushioning will only allow a corresponding amount of component travel to go along with that. The majority of the over-the-road force spectrum is under 100,000 pounds, where selective cushioning will limit movement to plus or minus 1.5 inches. A conventional hydraulic cushioning unit won't offer any deflection or energy dissipation until you overcome the preload built into the internal valving, nominally 100,000 pounds as well. Note that this does not include any free slack or passive draft, which generally gives you up to 3 inches of slack in each end of the car. Once you overcome the nominal preload of a hydraulic cushioning unit, sustained forces over the road will allow for full stroking of the unit, where selective cushioning still hasn't moved more than 1.5 inches. Remember that as the force reduces, selective cushioning's solid-state design will push the unit back to its neutral position. A hydraulic unit will slowly return to its neutral position over a minute or two from its internal pressurized nitrogen gas, but is more frequently pulled back to its neutral position by the in-train forces developed over the road. When a conventional hydraulic unit is pulled back to its neutral position, there's little protection offered for the knuckle. Often this results in a hard snap felt in the connection to the next car. And remember that selective cushioning offers up to 3¼ inches of smooth-acting draft protection for the knuckle in this direction as well. We've been conducting train action studies with various Class 1 railroads, 2 of which we're going to review here. The first scenario laid out on the right involves a 100-car coil steel train, which has 15-inch EOCC on each car. That number of hydraulic units generates up to 275 feet of free slack that train can shrink and grow as it goes down the track. This consist produces frequent broken knuckles at the rear of the train. Operationally, it's been proven that if you limit the train to 80 cars, the knuckles don't break. Why? You can see that as we sit at the bottom of the hill, all the cars are bunched together with the cushion units compressed. And as we negotiate the next hill, which only goes up about 35 feet over a mile or so, you'll have the head-end locomotive stretching out the front of the train up the hill and gravity pulling the rear of the train back down the hill. As this happens, these hydraulic units are being snapped back to their neutral position one at a time in a lengthwise freefall. And when we run out of travel, we have car 74 moving 4.5 miles an hour faster than car 75. Imagine a 4.5 mile an hour impact with zero impact protection. That is what this knuckle is absorbing as it ascends each hill. Now this behaves like cracking a whip at the rear end of the train, generating forces above 300,000 pounds in the rear third. Now that isn't enough to break a knuckle outright, but a service fatigue knuckle has been proven to be more easily broken by forces exceeding 283,000 pounds. We reran this coil steel train study with the same cars, same track, same handling, but swapped out the hydraulic cushioning units for Strato's Selective Cushioning System. The same conditions exist as we negotiate this hill, but as the force levels decrease, the actively neutral-seeking design returns to its neutral position on its own. This prevents the overall velocity wave from developing through the consist, managing the energy transfer more effectively during runout and extending knuckle life. The second scenario we've modeled consists of 42 auto-rack cars leading a large block of 92 intermodal platforms. The lesson we learned from the previous study was that ride quality is better at the head end of the train than at the rear, so why not put the more sensitive cars at the front? Well, with the weaker 921D hydraulic units in these cars, this is similar to using a slinky to pull a 6,500-ton bowling ball down the track. We do have distributed power in this situation, and as we crest this hill, the train is stretched out tight in full draft. As the head end descends the next grade, you can see we're still throttled up. The heavy rear end of the train still hasn't come up over the hill yet. When this center of gravity does reach the top of the hill, you'll see that the forces balance out before creating a rush down the opposite side. But by the time the brakes are applied, it's too late, and the weaker hydraulic units allow a large amount of energy to be generated with little resistance before the whole train goes solid. Now, this large amount of compressive force has to go somewhere, like squeezing a water balloon. This results in a gauge rupture between the last auto rack and the first double stack car, rolling the rail itself outwards and pushing the cars off the track in a derailment. As before, we reran this train action study with the same cars, same track, same handling, but swapped out the hydraulic cushioning units for Strato's Selective Cushioning System. Due to the train makeup, we have the same weight distribution throughout the consist, so gravity is still going to pull that heavy tail end down the next grade. However, the solid-state design of selective cushioning only gives the travel needed for the forces generated, more effectively managing the violent run-in event and preventing a derailment in this case. The selective cushioning unit does have AAR conditional approval for open interchange service, with our oldest units in the field for over 2 years right now, and we're actively expanding our install base on new and retrofit applications. As I said at the beginning, my name is Jonathan Sunday, and I'm Strato's Chief Engineer for Draft Systems. Feel free to contact myself or your local Strato sales manager for more information on this project or any of Strato's other solution-oriented product lines.